right. So this section is on the real zeros of a polynomial function. So the first question is, can anybody tell us what a rational number is? Okay, it's a fraction, a number that can be written as a fraction. Okay, it's written as like a over b, and a and b they're integers. Okay, so can anybody give me an example of a rational number? 1/3. 4. 4 is a rational number. What about -2? Is that a rational number? -2/1, right? Okay. What about e? Is e a rational number, or pi? Or sorry, e or pi. Okay, those aren't. Okay, those are irrational numbers, kind of like radical 2. Those are numbers that go on forever and they don't repeat. Okay, so if we think of this as a decimal, this is 3.14159, blah, blah, blah. It goes on forever and never has a repeating pattern to the numbers in that decimal. Okay, so rational numbers, if we'd made them decimals, they'd stop like 0.5 is 1/2 and stuff like that. 1/3, 0.3 repeated. Okay, so a rational number is a number that can be written as a fraction. Rational numbers are pretty nice numbers to work with, relatively speaking. Okay, so in the last chapter, in chapter 4, most of the polynomials that we dealt with were already factored, or they were really, really simple to factor. They were like quadratics or something like that. Okay, and if we know the factors, then it was really easy to find the blank intercepts. In other words, the zeros of the polynomial. What goes in here? X-intercepts. Okay, X-intercepts, zeros, solutions, roots, whatever words you want to use. Okay, and then it was really easy to graph it based on what we knew the function looked like. Okay, if the polynomial isn't factored, okay, then it's a lot more difficult. Or if it's degree 3 or 4 or 5, then it's kind of tough to work with. Okay, so in this section we're going to learn a bunch of theorems. Can anybody tell me what a theorem is? Kind of like a formula, what? Something that you use multiple times. That's correct. Okay, a theorem is a fancy word for, it's a mathematical rule that's been proven to be correct. It's been proven to be true. Okay, so we're just going to use we're going to learn a bunch of theorems that have already been proven to be true, and they're going to make our lives easier because we're going to be finding the zeros of a polynomial. Okay, so we're going to use some new information along the skills that we've already learned, like synthetic division, which we just practiced, and what formula? Quadratic. Very good. So we're going to use synthetic division and the quadratic formula to completely factor polynomials that until now, I mean, if we showed you some of the polynomials that we're going to be dealing with, they'd look impossible to find the zeros of. They'd look impossible to factor, and yet we're going to be able to factor them. Okay? So if you remember from 5.1 that if the remainder is 0, then the divisor is a factor of the dividend. Okay? And it would be nice if we had another way other than going through and doing synthetic division or something like that all the time in order to figure out whether it's a factor, and we do. So here's the first theorem. Okay? So again, what is a theorem? It's a mathematical statement that's been proven to be true. It's a mathematical rule, if you want to think of it that way. Okay? So theorems are often, they're very wordy. Okay? Sometimes they're hard to understand, but if we break them down into pieces, hopefully they're not too bad. It says, let f be a polynomial function, period. What this is saying is we're dealing with polynomials. We like polynomials. They're pretty easy to deal with. So that first part is just let f be a polynomial function. We're dealing with polynomials. If f of x is divided by x minus c, which a lot of times we'll write that way, then the remainder is f of c. So this is what we think of as the divisor, or what we hope is the factor. What it's saying is the remainder is exactly the same as the function value at that point. Let me say that again. The remainder is exactly the same as the function value at this point right here at c. Okay? So we're going to find the remainder when on this polynomial function. Notice we're dealing with a polynomial. If we're divided by this one and this one using synthetic division, which is a pretty quick process. Again, all we want to do is just find the remainder. Okay, just the remainder. So in the box, we put a 3. We write down a 1, a -4, a 0, and a -5, right? And then it's that same process. Bring down, multiply, add. Multiply, add. Multiply. We get negative 14, is that right? Okay, so there's the remainder. That's it. That's all it asks you to do. Just find the remainder. So if we do this one, there's a negative 2 in the box. Again, a 1, you can just copy this list down, negative 4, 0, and negative 5. Bring down. It's a pretty quick process, right? Bring down. Whoops. Multiply, add, multiply. It's going to be 12. That's a 12. That's a negative 24. So negative 29. There's the remainder. Any questions? Good? Okay, here's the cool part. Here's the theorem. We already know how to do this. This theorem says, you know what? You can figure out what the remainder is by just plugging in this number right here. The same number that we'd put in the box. So let's figure out what f of 3 is. F of 3 would be 3 to the third minus 4 times 3 squared minus 5. So this is 27. This is 9 times negative 4, so that's going to be negative 36 minus 5. So that's going to be 27 minus 41. Difference between 41 and 27 is 14. The bigger one's negative. Matches up. So you can figure out the remainder not by doing synthetic division, although that's one way to do it. You can also do it by just plugging that value into the function. So if we were doing this one right here, what would we plug into the function? We'd plug in negative 2. So let's see what f of negative 2 is. What had it better be if this mathematical rule that's been proven to be true actually works? Better be negative 29. Okay? So this is going to be negative 2, and I'm going to put that in parentheses because I've got to cube that, minus 4 times negative 2 squared minus 5. So this is going to be negative 8. This is going to be negative 16, is that right? Minus 5. That makes negative 24 minus 5, so we get negative 29. So, does this mathematical rule work? So here's another way to check and see whether or not it's a factor. You could just plug it in and see if the function value equals 0. Okay, listen, almost done. This is all I want to do today, but I want you to think about this. What's the 0 that comes from here? X equals c, right? Okay, that means it's a 0. That means it's an x-intercept. That means it's a solution or a root. If it's on the x-axis, what's the function value there? What's the y-coordinate? 0. So doesn't it make sense that if the function value equals 0, that's got to be a factor? Okay, so just let that sit in your brain. Let's let that cook overnight. Make sure you're done with 5.1. Let's correct that tomorrow because that was so easy. Let's correct that at the beginning of class, and then we'll get started in finishing up 5.2. Thanks. Have a great day.